So, good afternoon. Welcome to my talk. So, I'm Li Wang from DiDi, the cloud storage team. I'm very happy to have this opportunity to share our team's work on the librbd optimization. So first, let's give a brief review on what librbd is and what it does. So this slide shows a safe block solution for the virtualization scenario. For the data flow, as we can see showing the picture, so the disk access request issued by the virtual machine will be passed to the qemu+librbd. The qemu+librbd is a backend block driver of qemu. And then the qemu+librbd gonna further pass the disk access request to librbd. So librbd just sits between the qemu and the CIF, and it's simply relay the request and the response between qemu and the CIF. Okay, librbd sends a request over network to CIF, bypass the host kernel disk I/O stack, as the picture shown. So next slide will give a review on the safe block solution on the container scenario. So this picture shows the data flow. So the disk access request issued by the container will be first passed to MBD, which is a kernel block driver running inside the host kernel. And when it intercepts the request, it will simply forward the request to RBD-MBD, which is a daemon running in user space through socket. And then RBD-MBD pass the request to CIF. So actually, in fact, there was another solution. There was another safe block solution we didn't mention here, so that is to use the RBD kernel driver. And in that way, the librbd will not be used. So our talk will not cover that situation. Okay, so next, I first introduce our first work, the RBD iops optimization. So here comes the motivation. We did the FIO, 4K random write test, and surprisingly, we found that the RBD iops not scale in spite of the OSD number of the cluster. I mean, on the full SSD cluster. So the iops is bounded at around like 22K. No matter how many OSDs involved in the cluster. So we look into the codes, and we found the reasons. The reasons is when the RBD cache is turned on, the data will be first written into RBD cache by the writer thread, and then asynchronously flashed by the flasher thread. Both the writer thread and the flasher thread are single threads. And the most important thing and the worst thing is the writing and the flashing job, they cannot be paralleled. So the writer thread and the flasher thread, they are just mutually exclusive by the RBD cache lock. It's a big lock. As we can see the codes showing in the two figures at the bottom left, the codes show the work of the writer thread. So before it does the cache write, it will grab the lock. And as the figure on the bottom right shown for the flasher thread, before it starts its job, it also will grab the same lock. So the two threads, they just cannot be paralleled. So the lock held during throughout the flashing. And according to the CPU flame graph, so it's like the flashing job is time consuming. It's just consume much CPU time. And you can imagine during this time, the application write cannot be what is blocked. since it cannot get the lock, since the lock is scaled by the flusher thread. So as we can imagine, the IOPS will not scale. So how to solve this? So our solution is first enable the flashing work could be paralleled with writing. So we move the flashing, the major job, the flashing outside the lock. And the second work, we improve the flashing throughput. We revise the single thread design to multiple threads design. So here are our performance test results for the FIO 4K random write test. The IOPS can now, okay, I forgot to mention the FIO test was done in the virtual machine. So the IOPS can reach like 38K, improved by about 71%. So if you are interested, you can follow our PR as shown here later. Okay, this is our first work. So the second work is like the client-side image cache. So the motivation is we want to make advantage of make use of the RBD clone to save space. So in the virtualization situation, many virtual machines, they just share the same operating system and the applications. So we want to use the RBD base plus clone the technology to back the virtual machine's system disk so that we can keep only one copy for the read-only operating system data. So that's so that we can save space. So that we can save the storage space. So all the virtual machines, if they share the same operating system, they will use only one single base image. But they store their different data into their own clone image. In that way, we can save the storage space, but at the downside, it's gonna introduce another severe issue. It's the boot storm. So if hundreds, even thousands of the virtual machines with the same operating system boot at the same time, that can happen because maybe these virtual machines belong to the same tenant. So they may just start simultaneously to do some work. At that time, very high I/O pressure will be on the one single base image. The virtual machines will get very slow boot, very bad user experience. So how to solve this? Our idea is we store the operating system template in a qemu+librbd format file. And we just place the file at the computing node. We put it as a computing node. So we revise the librbd codes. We enable it to fast the qemu+librbd file. Okay. At that time, when the virtual machines, when librbd access the base image, will need access the base image, it can just access from the computing node locally. It can just access directly from the qemu+librbd file placed at the computing node. So in this way, the benefits are the virtual machine now can boot almost locally. They just read the data from the computing node. The I/O will not fall back to the safe cluster. So the I/O pressure on the safe cluster will be greatly reduced, and the boot speed of the virtual machines will be greatly improved. And also this approach is relatively very simple and straightforward and easy to implement. I mean, compared to some I know some other community work like client-side persistent cache something. We do a more conservative way. We just do the read cache. We just cache the operating system data, the read-only data. We will not do write cache. We will not do write cache. We just benefit the read operation. Okay, our third work is the librbd CPU overhead optimization. So the motivation is, according to our FIO 1 megabyte sequential write test, we found the librbd causes very high CPU usage. It's like reaches 124%. So as the CPU flame graph showing on the bottom right, you can see two obvious the hot spots. So the two hot spots are actually two mem copy. Now let's look at the two mem copies carefully. So the first mem copy is issued by qemu. So why qemu call this mem copy? So qemu calls the AIO write-away API to call librbd AIO write API to pass the data from qemu to librbd. However, unfortunately, for the librbd API, the RBD AIO write, it can only accept one input buffer. However, qemu holds multiple buffers, like a vector of buffers, so that qemu has to perform a memory copy to collect the data from its multiple buffers into one single buffer to match the requirements of the librbd API. So this is how the first mem copy comes. Okay, how to remove this mem copy? So we found that the librbd library installed by default by CentOS is actually relatively old. The recent librbd, it has already provided another API called RBD AIO write-away, which accepts multiple buffers. So if we upgrade the librbd and we do a little bit change to the qemu code to enable it call the new RBD API, the RBD AIO write-away, so that qemu can directly pass the buffers into librbd without that copy. So it's like the gather write optimization. For the second mem copy, it's issued by the librbd itself. So why librbd calls this mem copy? It calls a mem copy to copy the multiple buffers passed by the qemu to one private buffer. So why it bothers to do this? Since the data are asynchronously sent to OSDs by the librbd messenger module. So we were thinking, if possible, we eliminate this mem copy. We just let the librbd to refer those buffers directly. Why not? Why not do this copy? So the key is to, if we do that, if we do like the zero copy optimization, we have to make sure the buffers will no longer be referred by librbd after the write completes, since the buffers are owned by qemu. So if the write completes, then qemu may free those buffers. So after that, if we still refer those buffers, of course it's the program gonna be abort. So let's take a race condition example. Suppose first librbd construct a request X to send the data to OSD 0. X is on the way to the OSD 0. At that time, the network to OSD 0 temporarily down. So as we know, the heartbeat mechanism will make the safe monitor know this. It will think the OSD 0 is done, so it will issue a new OSD map to exclude the OSD 0, and it will issue the new map to all the members, to all the class members. So the librbd at the client side will be aware of this. So librbd will reconstruct a request Y to resend the data to another OSD according to the crash, because the crash map changes. So it will resend the data to, like, suppose OSD 1, and the Y completes. The buffers, it means the write has been completed, so the buffers will be freed by qemu. After that, the network recovers, X completes. So the messenger is not aware of all the things. It will refer the X buffer, but that buffer has already been freed by qemu. So the OSD will done, sure. So how to optimize the second mem copy? We want to use the zero copy optimization. So we implement the console request logic for the messenger module. So it's when the librbd reconstruct request to send to new OSD target, it first call the messenger console API to console the pending request first, to make sure those requests will not be referred. Those pending requests will not be referred later. Okay. Actually, recently we have made some revisions to implementation. So the idea, the first is to use the console requests, but now we have made some revision to the implementation according to the reviewers' comments. Instead of consoling the requests, we introduce a callback mechanism for the librbd. But the idea remains the same to do the zero copy. So if you are interested, you can follow our PR. However, this approach has some limitation. It cannot be used if the RBD cache is turned on with the writeback model, since the reason is obvious. Since in that situation, the data just be after the data written into the cache, the write completes, and the qemu thinks the write has completed. But when the messenger touch those data later, those buffers may have been freed by qemu. So the zero copy optimization cannot be used when the RBD cache is turned on with the writeback mode. That's the limitation. Okay, here this picture, this slide shows the overall results. So for the 1 megabyte file sequential write test with above the two optimizations, yeah, the latency reduced by 46%. iops increased by 85%, and the CPU usage reduced by 53%. As we can see from the three pictures from the left to right, the first is with the two memory copy present, and the middle one is we remove the first mem copy, and on the right side we have removed all the two mem copies. So as we can see, low obvious hot spots left. Okay, as the last part, I want to share some our experience with the community. Well, actually, there are some bad experience to our side. So the first is the latency issue. So according to our experience, actually the latency of Ceph is relatively high, especially for the Bluetooth nodes on full SSDs. So for the FIO 4K random writes with IO depth being 1, the average latency reaches like nearly 2 milliseconds. As we know, for the raw SSD, the hardware, if we just do the test on the raw SSD hardware, the latency like 100 microseconds. So it's got the latency compared to SSD's natural latency. It's relatively high, and it will prevent some critical applications from using SIF, like a database or some other latency-sensitive applications. So for this issue, we do want to collaborate with the community to improve it. And the second is the hardware utilization. So it's like the file stores on HDDs, more exactly on mix of SSD and HDDs. Since we place the journal of file store on SSDs. So according to our observation, when the average disk LUTL reach more than 60%, only 60%, the long latency, even slow requests may easily occur. Even with carefully tuning of the writeback throttle, something like that, the parameters. So yeah, this is since to our customers, they always care the price. I know the community gave much efforts on the new hardware like NVMe, like Optane, Intel Optane. But for the customer, they always care the price, and the price is always one of the major their concerns. So they always want to get the SSD performance on the HDD price. So we do suggest that the community could give more attention on the file store on HDD's performance, on the SIF on HDD's behavior, the performance. And the last one is the CPU usage. So for the Blue Store on SSDs, the CPU usage is high, and one SSD could only contribute like 11K IOPS, as compared to the raw SSD IOPS power, it will be like 60K IOPS. But under the SIF, it can only contribute 11K. So, and we found it's CPU bound. The CPU is a bottleneck. So we do hope the community could do more work to improve this. Okay, here now it's a talk from me. Any questions? Thanks. I think maybe have a microphone. Since, yeah. Okay, maybe, yeah, can see.
How did you implement the image cache?
Sorry?
How did you implement the image cache? You talked about the image cache
Yeah.
but you didn't have a pull request or anything, or a software example. How did you implement that in DiDi?
How do we implement the image cache?
Yes.
Okay. So I have mentioned. Okay. Hello. Just as I mentioned, we keep the base image. The base image. We keep all of its data into a qemu+librbd file. Do you guys know qemu+librbd file? Yeah. Yeah, we just store the base image, all the data is originally stored in the base image, right? We use base plus clone to provide the system disk. But instead, we don't use the base image. Not say we don't use base image. We store all the data of base image into a qemu+librbd file, and we place the qemu+librbd file at the computing node. The computing node means where the virtual machine is running. Yeah. And we revise the librbd. We revise librbd, and when librbd decides to access base image, at the first place, it will now instead access the qemu2 file at the computing node. It will not access self. It will not access self. It just access the qemu2 file locally from the computing node. That's how our cache works.
But how do you achieve that?
We revise the librbd and we use some like a third part the qemu2 parsing library. qemu2 file. Since we need to parse the qemu2 file, since the qemu2 file format is different from the raw format used by the RBD. RBD uses the raw format, and the qemu2 itself is a different format, file format. So we enable qemu2 to parse a qemu2 format file. Any further questions? No questions? Okay, thank you everyone.